This is everyone from EAFIT University, and we are really glad to have you here and to have this opportunity for you to talk about aerospace science.
Okay, my English is not the best English, but there is no problem because I can get in contact with my friend, with us, and you can support me also if I say anything really strange. Wrong. Jeroslav, I met Jeroslav 2 years ago and a year ago too in California University in a conference of CubeSat small format satellites. Yes. Jeroslav is the team leader of the CubeSat team from the University of Prague.
It's working?
Yes, it is working. You can talk.
Yes, I can hear a little bit of echo, but yeah, I'm down here. So basically, thank you for coming. This meeting. It's very nice to see all people interested in aerospace, in engineering, and in the same field as I have. So basically, I'm a student, the same as you, I'm 27 years old now. But approximately 4 years ago, I decided myself to build a satellite, to don't listen to people which told me it's not possible, it's too expensive. I simply followed my dreams, and this is a part of the research. So this small cube was is 33 kilometers above the Earth, and I can say that so this was I will have 33 kilometers above the Earth, and I can say that it was higher than I will ever be in future, because I will not be an astronaut. But this cube was higher than me, so it's really very big for me. Basically, I took my presentation from the flight results from the stratospheric balloon. Basically, the balloon is in this bag. You can see maybe that it's really shrouded. It's just a piece of plastic. Probably you know it. So the balloon which took my CubeSat or our CubeSat stratosphere is here. We found it together with the CubeSat, so it was really a success. Basically, the beginning was a little bit worse. This is the 2-unit CubeSat structure I made by my hands at home by very stupid tools. But this was the real first piece of hardware we had to fit the electronics and so on. I just want to check, can you hear me well? Can you hear me well?
Yes, we hear you okay.
Okay, fine. Yeah, among others, of course, the structure is just a piece of aluminum. So if you are good in machining, if you are good in CAD design, you can produce your own structure for very low price. For example, this is the solar panel. You can see the crack here. It's really sensitive to any touch, so maybe I can blow it more during this talk. It's a 2-watt solar panel based on just pure silicon solar cells, which are not good in these days to fly to space because its efficiency is just 10%. I can see the light behind me. Okay. So this was the first solar panel we had in our project. I bought it or made it for just how much? $50 approximately. So you don't need too much money to start if you want. So this panel was designed to be fit on the 2-unit structure, as you can see it maybe like that. So the first 2-unit structure and solar panels were developed 2 years ago. And then we started to realize that we need rocket, of course, to fly to space. So this is a piece of rocket. A bunch of my colleagues in Europe had the chance to fly on this Vega spacecraft. This is the European spacecraft, very lightweight, but with the maiden flight with this rocket, 5 CubeSats were launched. Unfortunately, 4 of them were not working ever, just 1 was working properly. So, it was just 20% of success, but it's a project, why not? And of course, we started to make smaller satellites, not just 1 unit, not just 2 units, but we realized the price of the rocket and so on. So this was the first structure which was made, probably Andreas know it, as a copy of the model which you can download it on the website. It's the ASIS CubeSat structure, but we need it for the fit check. So, for example, this board you can see maybe here, it's the onboard computer and a lot of things inside. At first, I would like to say we decided to build each subsystem at our university from scratch, because you can spend the same money if you buy it on the market, the same money you spend if you will develop it. But if you develop the subsystems, then you can learn a lot. So that was our approach, and it's working. It's fine. Okay, so I would like to talk about a little bit of some experience we had on the stratospheric balloon. So I'll switch to the screen sharing, and I will talk about a little bit like that. Can you hear? Can you see the screen?
It is loading, but yeah, apparently we can see it.
Okay. Now?
Yes, we can see it, okay.
Okay, so that's the background of this image was taken by a camera. It's not so sharp, but it's our view from the top, from the edge of space. So now the post-flight meeting was held one week after the launch to see people what measured and so on. So I would like to show it as well. The objectives of our satellite are quite simple. We would like to test by flight and investigate results of the first so-called space-friendly CubeSat subsystems, which means the attitude determination and control subsystem, onboard computer, electronic power supply, and communication subsystem. As a part of my PhD thesis, I would like to test the electrical power supply reliable circuits, which are intended for the mission called CHOOSE, which will be flying to the Jovian system, hopefully in 2022 on board the ESA, European Space Agency spacecraft. The instrument is called RPWI, Radio and Plasma Wave Investigation Instrument, and I'm the technical lead of the low voltage power supply, so that's the reason why too many power supplies are around me. And we would like to develop hardware intended for long-lasting deep space missions, but for a cost price, mean commercial off-the-shelf components, because you can, if you consider the radiation, if you know how circuits works in space, you can build your space-grade systems for a fractional price. You don't need to buy so expensive components from the United States, for example. Okay, so this was the proposal of our setup. You can see, can you see my mouse, the pointer?
Yes, we can. Yes.
Okay, so the balloon cord, the parachute, a long string, long, approximately 20 meters. This was the box for the thermal control, basically containing the batteries and some thermostatic electronics, and our CubeSat here, covered by the plexiglass panels to protect the solar panels against the rupture. And we tested the antenna, dual band communication antenna deployment. Probably someone of you already saw the video on YouTube with the deployment. And because the antenna was stowed during the flight till the deployment, we needed some communication antenna to download the data before deployment. So we carried some UHF communication antenna attached to the CubeSat, which will never be in space, of course. It was just for the balloon purposes. This was how it looked like. So you can see the thermal control box on the top with the camera here, looking down in the thermal protection coating. It was working throughout the whole flight in the environment with minus 50 degrees Celsius, so it was a little bit of a miracle that it survived, but it was calculated to survive, so it worked. And our CubeSat here, on the bottom, this box is just a charger, a little bit bigger charger, I know, but it's the laboratory power supply to feed the batteries inside before the launch. This is detail. You can see the UHF antenna here mounted on the Chinese chopstick. Never throw away after the lunch. It's useful tool to attach some hardware if you need a piece of a boom on your CubeSat. So this is our CubeSat covered by the plexiglass. You can see the shines from the ball above, and yes, and the red power cable was intended to heat up the internal heaters in the CubeSat. So we had some kind of cheating inside to increase the temperature, because normally the electronics cannot survive the stratospheric conditions, because minus 50, minus 60 degrees for a long time is never in space on low Earth orbit. So we used this kind of cheating to survive the flight. This was one of our colleagues holding all the setup. This experiment was for something different. You can see the GoPro camera here. What is interesting, the GoPro camera was working just 45 minutes or something like that. Our camera survived the whole flight. So if you want to fly to the stratosphere, always consider if you will use the camera or not from the top. Okay, so the CubeSat here, the antenna, communication, and our mobile ground station. You can see the balloon which is already filling with the helium here, the 23 dB antenna on the top of the car, aiming to the CubeSat here, and a computer which probably you cannot see because it's too dark in the car. So we are completely mobile, and we tried to follow the balloon on the ground track. And these are some preliminary results from the measurements. It's plot full of colors and lines. However, you can see zero here, zero, and this y-axis means the current. If the current is positive, the batteries are charging from the solar cells. If the current is negative, then the batteries are just discharging. So during whole flight, you can see that batteries were charging. What is interesting, on the ground, they were charging a little bit more because of the ground albedo. In the stratosphere, you have darkness around you, so then the current goes down and down to some certain limit, which is defined by the surrounding light on the sun. But it was working. It was measuring that, okay, our solar panels were charging the batteries. So that was really good. This is the voltage plot on each solar cell. You can see that it's almost the same because it was rotating slowly during the flight. And this brown plot, if you can see it, I don't know, maybe not. This plot was just a little bit experiment, just a small experiment. This is the unconnected input of the multiplexer, the AD converter. We had analog to digital converter on board board the CubeSat, which was measuring the voltages, and this was the plot taken from the pin from the microcontroller, which was not connected to anything. You can see that we were able to measure something, even if it was disconnected. This was probably made by some charging or maybe slightly due to plasma around, I don't know. But you can see this is something like this time, up to this time is the climbing and then going down. So you can see the very fast difference in the voltage captured on that unconnected pin during the deep freezing. Because in this region, we were going down at the velocity up to 250 kilometers per hour. It was a free fall, and we were passing the stratosphere with all the temperature down to minus 45, 47 degrees. So quite interesting what you can measure on the input if you don't have anything connected to your microcontroller. Yeah, this was the plot of the power supply, which were producing the 5,000 millivolts here. So it was the constant till deep freezing, and then again recovery. So we had a death of the power supply for something like 2-3 minutes because of very deep freezing. So what is really nice that it recovers. It was recovered, and now we know what was the reason for that malfunction. But this 3.3 volt was constantly measured even in the deep freezing, so no problem. This is probably the most interesting plot taken from the launch, so something like 12-13 degrees in the morning. It was 7 a.m. in the morning at the launch site, and then it was going higher a little bit because the balloon was heating up by the holding in hands and so on. And out in the launch, in this point, the temperature starts to going down below the 0 degrees, which you can see here in this axis, down approximately minus 16 or something like that, which was the threshold, the thermal control protections. So you can see that slightly the overshoot of the thermal control protection, and then the increase of the temperature almost up to the top of the altitude. So we were quite well protected by the thermal control protection which we designed. Yes, due to the brownout of the 5 volt, we had OBC, onboard computer restart after the antenna deployment because it consumed a lot of power. But then we had the data again, so you can see the climbing to the top altitude where the temperature was approximately 0 degrees, which is quite interesting. It was not minus 50, it was approximately 0. And then the burst of the balloon at the recovery, the flight to the ground at, as I said, 250 kilometers per hour. So almost minus 45.2 Celsius was measured at the minimum temperature inside the CubeSat, and then the landing again in trees on the ground. It was quite nice. So we ended up with 20 degrees on the ground again. Yeah, probably I can switch this. This was just a comparison between the voltage drop on the power supply and the outer temperature. So you can see some histories in temperature sensitivity, but that's not interesting for now. Then we had a measurement of the sun provided by the sun sensors. You can see some initial values here. A couple colors means 4 different sensors for the sun sensing device. Then the launch, and then a lot of peaks up and down caused by the tumbling of the spacecraft. And you can see that the average of these peaks goes to some certain value, which is down by the stratospheric conditions. So approximately till this point, the satellite was surrounded by a huge amount of light from the clouds, from the albedo of the Earth, from the sun, but then it started to go into the darkness with just a small piece of the sunlight in front. So we start these stuff somewhere here. Yeah, I would like to show the hardware in detail a little bit. So we made our own structure because we were not satisfied with the structures which you can buy on the market now. So it basically fits the CubeSat dimensions, of course. It's based on the aerospace aluminum. It includes the kill switch separation springs, the pinhole for the ring before flight key. And if you want it, if you consider, you can buy it. We are offering it now because it fits a really standardized boards which you can buy and can fit it inside. So if you want, we are able to provide it. Currently, we are working on the hard anodizing of the rails, as is mentioned in the CubeSat standard. What is basically the most interesting after the flight, which means after the recovery, no part of the CubeSat was lost, no part was damaged, and no thread damaged or no disk screws observed. So what we put to the space, it recovered back without any loss. So that was, we were really happy from that result. By our telemetry tracking and commanding subsystem, which is basically this Yagi antenna, almost 1.5 meter long, we captured 384 kilobytes of data on downlink, which was from 40 up to 90 kilometers, so quite huge, without any license, and it was let's say legal. So it was really nice to establish a link. We were not able to see the balloon, but the radio was, so that was really interesting. And yeah, this was I think the key success of that flight. This is the screenshot from the video, which shows the deployment of the strip antennas. You can see the stripes here, one and the second. The rest two are on the back side, which you cannot see. But if you check the YouTube video, you can hear for the first time you can hear the sound of deployment of the spring, because it has a characteristic sound. And then you can hear the reception of ground station or any mobile stations on the ground, which were captured by this antenna on the small walkie-talkie which was introduced in the gondola. So you can see the noise, you can hear the noise, you can hear the voices, you can hear the ringing of the calling, and so on. So it was very good proof that the antenna is working and that the antenna was deployed. There is a certain time, and of course we have to show it everywhere. So 28,200 meters of altitude, which was approximately 5 kilometers below the top altitude, but we were still in very calm region with almost no tumbling, and it was really nice to deploy the antenna wirelessly from the ground on our telecommand. So we were sending telecommand from the ground from this side, and the antenna above us, 28 kilometers above, was deployed. So you can see the video. Our future, what we plan is to fly to space, of course, to follow our biggest dream. To insert the CubeSat into the sun-synchronous orbit. We would like to fly to 600 kilometers altitude on Chinese Long March 2D launch vehicle, and because the SSO is typically, of course, passing through the poles, it will be a really good chance for tests of radiation reliability of the components, which is our main focus on the mission. Currently, we are talking and discussing with Chinese, and among others, we need to purchase a deployer. So a lot of things you need to manage before the flight. So probably the launch date be in the second half, probably maybe December, maybe November, no one knows, maybe September 2015. And if it will be everything working well, then it will be 7th Czech satellite in space since 1978. By the way, we had the 3rd nationality in space. Our astronaut was the 3rd. First were Russians, 2nd Americans, and the 3rd was our astronaut in Czech Republic. So the 7th satellite in space probably next year. So we shall start, and we're still looking for local flight opportunity. For example, today I received an email with offer to fly to the moon at a cost approximately $2,000 per kilogram. So if you have 200,000 kilo USD. So if you have $200,000, we can talk about it. And because we need to earn money, we would like to earn money for a flight. We started to produce some professional piece of hardware. So we made a company which is currently producing the first product. This is our CubeSat GPS receiver, which is the first ultra-low power receiver on the market. You can buy receivers with power consumption approximately 1 watt. But 1 watt, typically the input power, 1 unit CubeSat. So all the power you receive from solar cells, you will spend on the conventional GPS receiver. This receiver, our receiver, can work with just 100 milliwatts. So 1/10 of that power consumption. So even with the radiation shielding, you can buy this small, and I would like to sell it to earn money for our space flight. The second product, which will be very soon on the market, is solar panel with integrated GPS antenna, because you cannot buy it. You can buy a GPS receiver with 1 watt power consumption currently now on the market, but no one will tell you which GPS antenna, in which direction you have to put on your CubeSat to secure that it will work in space. That's not a simple task. You need to calculate it and test it. So this will be our second product. Then the power supply, as you heard about, currently we are working on the next generation, protected against the deep freezing. So now we know a lot due to the balloon flight, which was very interesting for us. And on this screen you can see the power supply, which is combined with 2 microcontrollers serving as onboard computer. Real-time clocks, 1 second, full module redundancy implemented with data memories. So one set, the second set, and basically these 2 cores are working in full redundancy. So if one is dead, then the second one is take of the responsibility and it works continuously. So that's our third product we would like to produce. And basically, thank you for watching. This is our current version. And if you have any question.
Okay, thank you. Yeah, we have a couple of questions from the audience. The first one is, what do you think was the biggest challenge when you build a satellite?
The biggest challenge, from my point of view, was to tell people that it's possible to make it. A lot of people told me, don't do it. It's too expensive, too complicated, you never win. So the biggest challenge was to claim people, okay, I will do it. Let's go together, let's make it. The biggest challenge.
Okay. Now that you have done the process and you build your own circuits, do you still think that it's better, or would you prefer to buy them and build in all together?
You know, this is a really good question. Sometimes you have to, if you are a project manager, if you want to build your own space project or whatever project, you have to consider which people you have around you, which people with which capabilities you have around, and you have to calculate if these people is better to pay for and to pay their expenses, and if this cost is lower or at least equal to the cost on the market, then make it by your own, because you will learn a lot. So there are some certain subsystems which are better to buy on the market. For example, the structures, sometimes the solar panels, because if you don't want to waste time and money with breaking the solar panels and buying new ones to learn how to do it on the PCB, then it's better to buy it, because then you save money. But if you want to learn it, make it by your own.
What not to do?
What not to do?
What not to do? Woo. For example, we don't have, if I can talk about myself and our team, we don't have, for example, the vacuum testing facility. So if you need to do this test, sometimes it's better to buy it as a service. So basically, I don't want to tell you don't do something. I would like to tell you make everything, but then you will be limited by possibilities, by time sometimes, by money of course. But money you can earn. You don't need to have some worries about money. Money are just a tool. So what don't to do? Simply, if you have feeling that you can manage it, you can manage it. If you don't feel that you will do it, then buy it or make it by some different people.
Okay. How is it the funding? How the funding has been for each of the launches?
For the balloon launches, you mean?
Yes. I think.
I can say again. Hopefully, it was kind of cheating, because we were in a competition which was announced here in our region, in Czech Republic and Slovak Republic, in Central Europe, and we won the flight. So we were on the right time, in the right place, let's say.
Okay, and finally, what kind of simulation has been done to the structure of the CubeSat?
Structure, we have currently the CAD software tool, which had some modules for the finite element methods testing. So we saw some plot and we saw the numbers about the margins, about the design margins, about the forces that it can survive. So we have a simulation done by finite element methods of that, and we found out that during the standard conditions in the P-pod in the rocket, or even on the ground tests, you can survive it by the structure, which is basically this structure.
And I think that will be it. If there are no more questions. Thank you very much.
Okay, Jeroslav, thank you so much. Na zdrowie. Okay. And okay, goodbye. Okay.